Right, let's continue where we left off. Share my screen. Today's lesson, we continue with Boolean Algebra, and we're going to talk of what we call universal gates. We introduced universal gates. We introduced the gates we've already seen being put into application, the AND, the OR. You need to know these are operators. These are called operators. We have not primary operators, these three. Then we have the nons, which are direct opposite of this. We have the no, direct opposite of this. Right, we also have exclusive or, we also have exclusive no. These are some of the gates we will be using. These are not universal. We are not on the universal part yet. These are the gates we introduced or we are going to introduce. What you need to know about these gates, probably what I want, what I will not be, mute yourselves, avoid being removed. All right. Now I'm disturbed. Where were we in Africa? I was saying what you need to know. Now that you have the operator, you need to know the truth table for each operator. Truth table for each operator. For example, AND. If I ask you to represent the operator AND using a truth table, I will tell you how many inputs it have. Most of the inputs, most of the operators we will be using for understanding purposes have two inputs. I can say input A and B. How do you design the truth table? 0, 1, 0, 1. If you have two inputs, then it means you have four possible outputs. 0, 0, 1, 1. You need to learn the way how to represent these numbers. When I go 0, 1, 0, 1, what exactly do I mean? With practice, you understand. Right. The output F, or let's say the output AND. The output AND. You need to deal with the truth tables. For an AND operator, AND gate is sort of a multiplication. So we get 0, 0, 0, 1. This is the basic stuff you need to know. Before we get into the bigger stuff, you need to understand this. These are simple stuff. You need to know how you can represent the AND as a logic gate. This is the AND logic diagram. The same with all these. You can do your homework and do the rest. Now, today we are going to talk of what we call universal gates. Now, not today. Now, universal gates. What are universal gates? And why do we use universal gates? Universal gates, we have NAND gate, what we call the NAND gate. We also have the NOR. NOR. These are both universal gates. Someone came with an idea that instead of using AND, OR, NOT, XOR, XNOR, all this in one circuit. Instead of using that, you can have a circuit with all this in one circuit. Instead of using different operators, different logic gates in one circuit, why not use the same for everything? So whoever that was came up with the idea, we can convert this AND into a NAND. We can convert this OR into a NAND, this NOT into a NAND, this one, everything into a NAND. So that I can make a circuit using only one type of logic gates. Therefore, the term universal. All the gates we have already mentioned can be represented using NAND only or N or NOR gates only. Now, NAND gate, two input NAND gates. What does it look like? We have A, B. Help me with the truth table, please. 0, 0, participate. 1, 1. NAND. What are the outputs? The first one. What is the output of that NAND gate?
1, 1, 1.
1, 1, 1, 0. We also have why do this? We also have no gate. What are the outputs?
1, 0, 0, 0.
1, 0,
0,
0,
0, 0.
0. Is this true? 1, 1, 1. Yes, this is true. This is where you start. Now you go to how do you represent the other gates in the form of NAND gates. How do you represent the other gates? For example, how do you turn a NOT gate into a NAND gate? Right. I know when I see one, this is how it looks like. That was the first thing I did. I claimed it. So here we have this is a NAND. Voila, this is a NOT gate. If I have an input A here, the output is A bar. I know first comes the claiming. This is where I started. I know. Now, understanding how you can come to this point. You have A bar. Your input is A. That's where you want to reach. Let me see. All right. Let me see. If I have a function f, which is A, not A, I can simplify this, right? I can simplify this using Boolean, Morgan. I can simplify this using the Morgan's theorem, right? I can get A bar plus A bar. True or false? I can get A bar if I simplify the whole thing there. So it means if I have an input of, if I want an output of a function which is A bar, how do I represent it using a NAND? This is a NAND expression here. NAND, it means you have A and B not. That's what it means. This is your starting point. I want to go to a NAND. But how do I go to a NAND if I only have one output, which is A bar? Which is A bar. So you start with A bar. First, we started with the claiming part. This is a NOT gate. So if I have an input X, I will have an output X bar. You can as well prove this using the truth table. It's true. Or I can start with, I want to get X bar. How do I get to the NAND expression? I know that X bar plus X bar is the same as X bar. I know I can simplify this using De Morgan. We have X, X, X bar. And there I have my NAND gate. How do I represent this function? It means I have one input X one input x is the same input as a NAND operation. The input is the same x. Here we have the input x. On top of that, we have a NAND operation represented by this x, y. This is the NAND operation, this and this. Let's move on to another one. Probably we get a clear picture of where I'm going. Let's have an AND gate. Let's have an AND gate. How do we represent an AND gate? Using OR NAND gates. Right. What is an AND gate? If I have two variables, A and B. This is an AND gate, right? Two variables, we have an AND gate. Now we want to use these gates only. This is an AND to represent the same thing we have here. How do we manipulate it? First, it comes the cramming. AB, this is how we represent it. We get XY here. I have a truth table to show for it. Some of the techniques I'm using, even to draw the truth table, you will need them. So pay attention. I can prove this is the same as XY, as AB. Sorry, this is the same as AB using a truth table. If I go at this point, I have two inputs, A and B. Right, if I go at this point and I call this point X, and I call this point Y, I have two other points, X and Y. Two inputs, it means four possible outputs. What do I have at point X? Using NAND operation. What do I have at point X? Yes?
0, 0, 0, 1, 1,
0, 0,
1,
1.
0.
This is 1.
0 mana 1.
Start again. NAND operation of A and B. I think
It's
this
one,
is
one,
1,
one,
1, 1,
1,
0. That is a NAND operation, right? Now we have that output X on another NAND operation. From the first one we gave, what does this represent? This represents cramming part. This is a NOT gate, right? Two inputs made one output of a NAND operation. This is a NOT gate. This is the first one we did. So I know this is a NAND gate here. This is a NOT gate here. So if we have a NOT from X to Y, what do we have? We have a 0, 0, 0, 1.
1.
Or you can do this if you are scared. Maybe you don't know what the NOT looks like. You can replicate these values. Put another X. We have 1, 1, 1, 0. Because here we have X, so it means we have X input, X inputs. Two inputs into a NAND operation. What is the output? Y. 1 times 1, this is 0, 0, 0, 1.
0, 1.
Right. Now, what is this operation here? Remove everything. If we remove this, if we remove 0, 0, 1, 0, 0, 1, 1, and we remove XX, we are left with Y, 0, 0, 0, 1. What does this truth table represent? This truth table represents AND function. So with this example, I've shown how you can prove an expression is the same as another expression given. Or is a logic does the logic diagram represent the expression given? I've gave you this logic diagram And I said it gives an expression AB. Can you prove that to me? One way to prove it is you go through the logic diagram. Give me these intermediate points and you prove your point. This is end. Now, going to how I can come up with this diagram here. How I can come up with this logic diagram here. All right. Where do I start? I start with A, B. This is an end function. I want to represent it using only nonce. Only nonce function. Now, this is the same as, it's the same function, right? Oh, let me do this. AB is the same as AB bar bar. Okay? It's the same. This, if I apply De Morgan's, is the same as A bar plus B bar on top another bar. It's correct, right? Are we together? Apply De Morgan for me, please.
It's correct.
Correct. Right. We can apply De Morgan again. We can apply De Morgan again. Where do we come back? We come back to this stage. Right. Now, and we have, let me say, this is an AND gate. We have an OR gate. We have a NOT. We have a NOT. We have a NOT. On top of that, we have an OR. Let me represent the OR gate first. Then I think you get a clear picture of how we go about representing the NAND. Yeah, just a minute. Let's start with OR. Let's start with OR to
No.
NAND, not OR. OR, not NAND. We have a nightmare. Let me see. A naught plus B naught bar. Can you do this? What is A naught? A, B. Let me see if I can find the solution for what I'm looking for here. A naught, A, B. Okay, let me come back to this later. You can excuse me on this one. Let me come back to this later. Let's go to the OR, because there's an OR here, which we are going to be using. So before I get to the end, let me go to the OR part. OR is a representation of only nonce. How do we represent it? Cramming part. Let's use X, Y. It's like this. Yeah, we have X plus Y. You can prove this using the truth table as well using the expressions. So this is X naught and Y naught. Right. So we have X plus Y. If I apply De Morgan's like this, I get X bar y bar, on top of that, another bar. So what do we have? In terms of NAND, we have something like this. This is the NAND, where we have two functions, let's say A and B. We have an AND gate and a NOT gate. Here, what we need is an AND gate and a NOT gate. So this expression basically represents a NAND gate. But a NAND gate of what? Yeah, we really needed to pass through the OR gate first. Right. Let me start again. How do I come up with the logic diagram of this one? How do I get there? What is an OR gate represent? What does it represent? It's the same as the expression x plus y. How do I simplify the expression x plus y so that we have something which represents and not? This is an AND. How do we go from this expression to an expression which represents this function and this function not? How we go to that direction, we can use De Morgan. We can use De Morgan. If I put two bars here, x plus y is the same as x plus y bar bar. If I can simplify this, I get x bar y bar bar. Now I have two operators I'm looking for a NAND gate. I have this operator, I have this operator. Now, it is a NAND gate on function of what of what inputs? Of the inputs x bar and y bar. So it's, if I am to draw a logic diagram of this, I can do this: x bar, y bar, NAND output. True or false? Anyone gets where I am here? Is this true or false? If I am to go from this expression here, using a NAND gate, I can draw it like this. I have two inputs, x bar and y bar. Function is a NAND. What do I get as an output is x bar, y bar, bar again. Anyone understand me? Very important, tricky, yes, but very important to understand where I'm coming from and where I'm going. No one does. Let me repeat. You need to know how to manipulate your functions so that you get logic diagram which is required of you. If I have an OR gate, I know it looks like this. But how do I get there? How I get there, I manipulate the OR expression, which is x plus y. Where is that? All right, be very careful. I manipulate the expression. I have x plus y so that I get it to be expressed as something with a dot and a not. This is an AND. When I started with, do we still have the not? When I started with not, the simplest of them all, I said not is represented by x bar. This is the NOT gate. If I have a function x, what is the output of a NOT bar of a NOT gate or a NOT operation? It's x bar. But for my example, I think I used a bar. I used a bar. How do we go from a bar to a function which relies only on NAND gates? I said it looked like this. I know it looks like this. If I have a here, I'll have a bar. But how do I get there? And I proposed A bar is the same as A bar plus A bar. And if I am to apply De Morgan's theorem here, this will be the same as A and A naught. Are we together? Feedback, are we together? No. If it's a no, I need a no. Not silent.
Yes.
All right. So once I get the operators I'm looking for a NAND, I'm looking for this and this. Then I can go draw a logic diagram. Once I have the dot and the bar, I can go on and draw the logic diagram. So my logic diagram, it says I have two inputs, A and A. So I can do these two inputs, A and A, with my NAND. I get A bar. This can be simplified as one input A. I get my A bar. You can prove this using the truth tables. But how do you get there? Because what happens is I'll give you a function A plus B plus A bar C multiplied by AB plus AC. You will be given a function like this. You have OR gate here, you have NOT gate here, you have AND gate here. And you are asked, represent that expression using NAND or using universal gates. You'll be asked to express this whole thing, give us the logic diagram using only NAND gates. How do you do it? You need to know this manipulation. That's why I'm putting a lot of emphasis on this. You need to learn that manipulation. So this is the manipulation for the NOT gate. And we are now on the OR gate. And I said the OR gate. You have two expressions. You have X plus Y. One expression with two inputs, X plus Y. This is an OR gate. How do I then manipulate it so that I get something like this with a bar with two inputs? I need an input here. I need an input here. How do I get there? I can use De Morgan. This is the same as X plus Y. This is the same as X bar not X bar another bar on top. So now I have my operators, the AND, this one, and the bar. I have them here, this one and this one. So what does it mean? It means I have two inputs. I can do this. It's sort of a shortcut. I have two inputs, X bar, Y bar, and this is my NAND. So my output will be X plus Y. This is true. But my original inputs, they were not X bar, they were not Y bar. They were X and Y. It means now I need to change this X bar to an input of X. I need to change this Y bar to an input of Y. How do I do that? X to X bar, this is a NOT gate. Y to Y bar, this is a NOT gate. How do I represent a NOT gate using nonce only? I already gave, this is a NOT gate using a nonce. So if I have X here, I will have X naught on the other side. So to have the input X, which I had here, and the input Y, which I had at the beginning, I use this gate and I input it here. So I'll now have, for X bar, I now have X producing X bar at this point. I now have Y producing y bar at this point. Now I have x bar here, I have y bar here. Then I continue, I take this one. The input is x plus y. This is an OR gate using NAND gates only. All right. Anyone who gets what I just did here, please, I just need one. I just need one. For the rest, you figure it out on your own. I just need one. Anyone who gets, thank you very much. We are done here. Then we go to the last one, AND gate. Representation. Yeah, let me see. This is the AND gate. It's X, Y, and so here we get XY. But how do we get there? De Morgan, same situation. AND gate solution is X, Y. If I apply De Morgan here, I can do this. This is the same as X, Y, 2 bars. This is the same as X bar plus Y bar. On top of that, we have another bar. I need to get the AND operation and the NOT. I have the NOT already, but I need the AND. If I apply De Morgan, which says A plus B bar is equal to A NOT B bar bar. What do I get from this one? I get X bar bar and Y bar bar. Is this true? X bar. Is
Yes.
this true?
Yes.
I get XY. I get the same. Or, but if I do this, is this the same? This is where I came from here. Right? X, Y, bar, bar. Let me separate it like this. I get where I was getting off the train. Let me separate it like this. We have our operator already here. We have our operator already here. And this is another NOT. How do we go from, we came from XY and we said it's the same as XY bar bar. We have a NAND already with this. What if I remove this? I only deal with the blue one. I only deal with the blue part. If I deal with the blue part, I have two inputs, X, Y, NAND, and we get an output. If I only deal with this blue part. Now, after that blue part, we have another NOT gate. This one. We have another NOT gate representing a NOT gate. A NOT gate looks like this. So if we have our output here, let's say Z here. Here we get Z bar. So our output here after a NAND gate is X, Y bar. How do we get X, Y bar bar? We put a NOT gate. I hope you get me. This is how you get to representing an AND gate with a universal gate. So we've represented 3 gates: the primary gates, the NOT, the OR, the AND. And I need you to get at least the direction of how I was doing things here. A bit underprepared, but we got the solutions. Now, when I give you an expression, I already gave out an expression here. You will be given an expression this big. Now you need to use the ways I was manipulating those numbers to get to NAND gates only. You have to find ways. Now that comes with practice. This whole thing can be represented using only NANDs. If I'm using the AND and the ORs and the NOT gates, it's very simple. But if I'm using the NANDs, it gets a bit complicated. So I gave you the background. I gave you the AND, I gave you the OR, I gave you the NOT. You can then do this on your own. And I think this is it with universal gates. So just to summarize, we did universal gates, NAND. We are still to do the NOR part. We are still to do the NOR part. We did the NAND, and we said why use them? Because it is easier. It is easier to build circuits using only one type of gate. In this case, NAND or no. It is easier using circuits with one type of operator logic gates. All right. This leads to faster switching. I think we'll get into this later on when we do our combination and sequential circuits, faster switching. The circuits that we build, they are used for switching. If you use all the primary gates and you have another circuit with all the NAND gates, you see the circuit with the universal gates will be faster than the one with the primary gates. It is also cheaper. It is also cheaper compared to using the primary gates. Now, and that summarizes NAND operation of the part my universal gate. Any questions? 1 minute. Any question? Comment. I think we can do another one. Yep. Questions, comments? Nope. All right. We are starting soon after. Question: which book are you using? I don't have books, unfortunately. The only reason I'm having difficulties explaining this one is the lack of preparing my head to give it out to you. I don't use books, unfortunately. That's why I cannot give you any.